In preparation for the exam this Wednesday. So today we spent most of the time on the one of the questions that might be tested in the exam. Okay. Yeah. Good afternoon. Good afternoon. Good afternoon, Bill, everybody. All right. So let me show you the class notes that we had last time a little bit. I would like to review that a little with you, and then we can move on from there. All right, so last time, we finished up the cost of quality topic, and then we move on to the SPC topic, right? So in the SPC, we focus on the gap number 3 in the gap model, where that gap 3 is the mismatch between the design specification and our implementation, right? Our produced units deviate or vary from the design specification, and is not wanted, right? All right, that happens because of many reasons, and we went through the framework of quality to classify all of the variables into 3 types: the input, the output variables, and the environmental variables, right? Input are the variables that we make decisions on. They are under our control. The output variables are the one that reflects or will lead to customer satisfaction, right? What the customer cares about when they buy our products and services, goods and services. And environmental variables are the variables that will impact, right, the relationship of input and output, right? So, and environmental variables are not under our control. All right, we can mitigate them, but it doesn't mean that we can get rid of them or change them, right? We can only mitigate the impact of the environmental variables. All right, and then next we talk about the 2 types of variation: the natural or common cause variation and the special or assignable cause variation, right? Natural variation happens because of the mix of many factors. So there's no way for us to single or separate one cause out so that we can do something about it, right? So that's why generally, we do not do much about the type 1, the natural variation. But of course, if you buy better equipment, invest in a new process, modern process, and then retrain the workers, and normally things are better, right? But with the special or assignable cause variation, we can separate the causes, and then with that, right, we can do something about it. In the short run, we can just fix it. In the long run, we can avoid it altogether, right? So that's the reason why we have to separate 2 types of variation. One is we cannot do much. The other is we can do something good about it. Okay. And next, I show you the ice cream shop example, right? So in this ice cream shop, the small variation here that looks quite regular, right? It is called the natural variation. But sometimes we see the special variation like that, and we ask ourselves, why does that happen? Right? What are the causes of the special variation? And if we can answer that, then we can fix it, right? And also, in the future, we can build robust processes so that we can avoid that problem altogether. We don't have to deal with that problem again in the future, right? All right. I add 2 more slides here in the overview of the SPC. So what is SPC? SPC is a quality control approach that emphasizes variation and statistical analysis, right? So we accept that the variation. And second, we use a lot of statistics to measure the variation, to understand the quality problem, to see what we can do about it, right? So that we can reduce the number of defects today, and we can make the process more robust in the future, so that we do not have any problems like what we have today anymore, right? And finally, I add another slide here. It is about the main activities of SPC. So in SPC, there are 4 main activities: capability analysis, and then capability analysis is just we calculate to what extent that we can conform to the design specification, right? Do we stay how much, to what extent, how much, or how much we stay true to the design, right? So that's the first activity. And then in the actual production process, we monitor the process to see if there's a special variation or not. And if there is a special variation, then we investigate it in the third activity here, right? So we investigate what is going on, the causes of the variation, so that in the future we can build a more robust process, right? And then by the end of this robust process here, our process is already better. So if you calculate the capability indexes, right, it should be higher than before. But of course, we do not end there. The next cycle, we also do that. We improve the process a little bit more. And then we do that the next day, the next week, the next month, and over the years, right? So this is a never-ending loops where over time we try to improve our process to make it higher and higher over time, right? So if we just keep improving our process, then it's going to be a very good process in the long run, right? And that's good for our quality. Okay, so that's the overview of SPC. It's not the end yet. Later on, we're gonna break the SPC down into bigger, big topics, big small topics inside SPC, so that we can go in more in depth about those topics, right? But today we need to switch to another related topic called Six Sigma, right? So Six Sigma is related to other parts of the homework questions and related to some parts of the SPC. So I would like to go to that first, okay? And that will be question 21 in our homework. And that might be tested in the midterm exam. So let me show you the question 21 in our homework. Very quick, let me find it. Okay, so I have the homework 2 question, homework 2 part 2 right here, right? So there are 5 questions. I already covered question 22 about the cost of quality and Pareto chart. Actually, just a friendly reminder that it is due tonight, right? That's question 22, due tonight. And then today we go over question 21, and question 21 is due tomorrow, right? So even though today, okay, we're gonna go through this question 21 in details, but I recommend you to work on this question, handwrite out step by step by yourself. Of course, you can always go back to the notes and match to see if your work matches with the class notes or not, right? But I would like you to practice with that question 21 because it might show up in the exam, right? Okay, so here's the content of this question. An online retailer carried out a random survey on shipments done by its order fulfillment department. In contacting 1,875 customers, the retailer tried to find out if there are problems with the shipment, right? So why an online retailers have to contact the customers to know if there is a problem with the shipment? Because you know what, only the customer know if there's a problem with the shipment, right? Only when they receive the shipment, they will know, okay, if that is a correct item or not. Is that damaged or not? And then when they try it, is that functioning or not, right? So only the customer knows. And to measure our quality, service quality, we have to contact the customer to find out if it is good or not, right? So again, we contacted 875 customers, and then the survey response rate was 75%. Because here we talk about customers, right? Not all of them will have the chance to answer our survey. So only 3/4 of them would answer our survey. They said I said here the two tables at the end will help with the question. So we have the two tables right here. They are short, okay, but there are two tables, right? The first table you do not need to have a look at them right now because there's some kind of typo with it. But the second table we can use it, okay? All right. So later on, I'm going to show you how to use a second table. The first table we just use that equation here in Excel directly to calculate the values that we need. So we do not really need this table. All right. So 21 shipments were found with the problems, and each of those shipment is considered an error. So find the defect per unit, find the EPMO or the errors per million opportunities. Right? Those are the new concepts that we learned today. And the calculated sigma level of the fulfillment service. Right? So we calculate three important things here in part A. So I hope you already know the information, right, of the question. Let me go through the question with you. All right, but before that, I would like to talk about the Six Sigma topic very quick, and then we go to the question. So we're in module 5 about quality management. And today we move on to the next big topic of Six Sigma. From time to time, you should have heard about it, right? So what is Six Sigma? Six Sigma is a business approach, or sometimes we call that as an ambition, where they try to aim to have the following with the goal of 3.4 defects out of 1 million opportunities. All right. Think about it. If somebody gives you $1 million in $1 bills, how long does it take to count $1 million bills? It takes a lot of time, okay? In this case, we talk about a business producing 1 million units, and they count it from the number 1 to the number 1 million. And at the end, they only find out there are 3.4 defects. Think about it. This is a big achievement right here. It's a very impressive process, right? Because they achieve near zero defects. So that's a very big deal. And of course, it's not easy. Companies, they have to spend millions of dollars in their process to improve everything, so that at the end they can achieve 3.4 defects. They can achieve only 3.4 defects out of 1 million units, right? So that's a very big ambition, right? So okay, so in Six Sigma there are two aspects. Aspects number 1 is about how to measure it. So that's a measurement of the sigma level. Right. So the sigma level eventually is just a number. It might sound very fancy. Sigma level, it sounds very technical, but actually it's just a number that reflects how good our process is. And we want it to be the higher, the better, right? So that's the measurement. We need to see how good our process is and try to improve that over time by having a higher and higher measurement over time. But then the question is how to achieve the higher and higher measurement over time, right? Or how to achieve Six Sigma. That's a big question, right? Because companies, they have to spend millions of dollars to achieve that Six Sigma. And if we want to learn about how to achieve Six Sigma, we have to take classes. So in our class, we don't have the context, we don't have enough time, then there's no way for us to deal with this in details, right? So, but I recommend you to read more about the GE's, General Electric's, DMAIC problem solving methods, right? This is an acronym for, so first of all, we need to define the goals of the process and then measure the performance of the process. What sigma level it is, for example, right? And then we need to analyze the data. After measurement, then we collect the data and analyze the data. And then if there is a problem, we need to investigate. And then at the end, we need to control the process, right? So that it will be better over time and we can maintain the performance over time of the process, right? So I encourage you to read more about GE's the MAIC method. That's how they can achieve the Six Sigma level. So some of you might ask the question that how come we can achieve 3.4 defects out of 1 million, right? But actually, in the reality, there are processes that are operating at that level. For example, GE's the airplane engine department, they have to work at that level, right? Because airplanes cannot have a failure in the engines. So so they have to produce the engines with nearly perfect quality, so that most of the time, nearly most of the time, the engines work properly, right? So for those processes, they have to work at the Six Sigma level. They have to invest a lot of money to route it up so that no errors will, or very few errors will come out of that process, okay? Six Sigma can be applied in manufacturing, in services too, in installation of new systems, things like that, right? Okay, so it has a very broad applicability. Let me give you the warning that the Six Sigma that we talk about here is different from the Six Sigma that you read in the book. In the book, the Six Sigma level, the Sigma level is how many sigma, how many standard deviation that we can squeeze in the design specification, right? So normally that is used for manufacturing. The Six Sigma that we are focusing on today is more broadly or is more generally defined. So it can be applied to many contexts. Okay, so today we will focus on the measurement of the sigma level, where we can use that sigma level to any process that that can be measured with the number of errors, things like that, right? Then we can calculate the Six Sigma for them. Okay, so that's the overview of the Six Sigma approach. And now today we use our homework question as one example for it. Okay, so our example here is homework 2, question 21, right? So in this case, the online retailers contacted this many customers. 1875. customers. We contacted this many customers. And then out of these, only 75% of them answered our survey, right? So, so we have a subset of the actual responses here. So these are the responses, and it's only 75% of the total contacts. So it means that out of 1,875 contacts, we can only find out about the quality of the shipment among those 75%, right? And of course, outside of these 75%, it is unknown. We don't know if the customers are happy with the shipment or not, if they have any problems with the shipment or not, right? So we only have data about the 75%. So when we have data, the actual data is called the sample. And we call the size of that sample as a sample size. So in this case, right, the sample size equals the number of contacts multiplied with the response rate, right? So it's very easy. We just take 1,875 times with 0.75. Right, then we have the number of orders that we know about, the statuses. Right, so we got 1406.25 orders where we know if they are good or not at the end, right? The remaining units, for the remaining orders here, we don't know about them because the customer did not tell us anything about them, right? So we only have the data here. We don't have the data here. All right, so that's the context. And now let's go through the parts A, B, C of the question. In part A, first of all, we in part A, where is that thing? Just 1 second, I thought I already. All right, so in part A, we need to calculate the defect per unit. Right, or DPU. Defect per unit is, it means that out of this unit, how much of that unit is defective, right? But later on, we can broaden it to say, okay, so out of 100 units, how many of them are defective? So in a sense, the defect per unit and the defect probabilities are the same, or the percentage of defects are the same. So let me show you the equation for this. The DPU equals the number of defects divided by the number of opportunities for error, or the number of units that we have in our sample, right? Okay, so we, in this particular context, we're gonna get 21 errors divided by the 1406.25, right? Then in that case, we're gonna have, then we have the following result, 0.01493. And to make it a little bit easier to grasp the number, we convert that to 1.49%, right? So we can call that as a defect per unit, or we can call that as a defect probability. Let me make a note right here. Or DP. I would like to ask the whole class, what is your personal take on this 1.49%? Is that big or is that small? Right? So 1.49% defective or 1.49% with errors. Is that big or is that small? Please feel free to share your personal take. Okay, so here, is that a C? Did you say small?
Yes.
Okay, good. Yeah, so a lot of people, I already see your answers, and you also say smart. Good. I only ask for personal take. I do not say right or wrong here. Okay. So good. So 1.4% is in the common experience in our daily life, right? 1.49 is smart. If you compare this to the mortgage rate, to the interest rate of the credit cards, is way small, right? It's not 10% or 15% or 20% or even more than that, right? Okay, but then we talk about this in the business context. Then you know what? In the business context, sometimes they produce millions and millions of units. For example, in a light bulb factory, they produce millions of light bulbs. In a hotel service, they have millions of contacts with the customers, right? In one day, one customer having contacts with your service, and then you multiply that with the number of customers, and then multiply that with 365 days in the year, then you should have millions of contacts with the customers, right? And each one of those units or contacts can be an error. And if we have 1.49%, then let's see how big the number of errors would be, okay? So to do that, we need to put the percentage in the context of 1 million units. To do that, we come up with a new concept called errors per million opportunities. Or EPMO. Or another way to call it is the defects per million opportunities, or DPMO. Okay, so in this case, we're going to call that as an EPMO because we talk about services, fulfillment services, right? But if we work on this in the manufacturing context, then normally we call that as a defect. But in terms of the equation, they are equal. They use the same thing to calculate the number, right? So sometimes we call it as EPMO, sometimes we use the DPMO instead. But in this case, right, EPMO and DPMO are the same thing, are equal. Okay, then it is calculated as a DPU that we got earlier, multiplied with 1 million. So we just got the number earlier, 0.01493 times with 1 million, right? Then the final answer is going to be 14933.33. So here is the number of errors per million. Think about it, right? If we are producing 1 million light bulbs and nearly 15,000 light bulbs do not light up, for example, then the companies will have to spend a lot of money to fix those light bulbs, or to scrap those light bulbs. Right? It costs a lot of money if we have this number of defects. Or if you think about Amazon.com, in one day they deliver millions of orders, right? So per 1 million orders, they make nearly 15,000 mistakes, 15,000 orders with errors. Then how costly it is? What do you think? How costly it is to remedy the situation for those 15,000 shipment or orders, right? That costs a lot of money. So I asked you earlier the 1.49% big or small. Possibly the most appropriate way to answer that is it depends on the situation. But generally, right, if we think about 1.49%, it's going to be a big number already in the manufacturing context, in the fulfillment context, like the Amazon.com process, right? Then 1.49% is a big deal because it means that the company will have to spend a lot of money to fix the problems, remedy the situations, take the returns back, and then send the correct items back to the customers, right? It costs a lot of money. So we don't want this to happen, right? So of course, in your actual business, in the actual context that you are working in, then you're going to know what would be the appropriate number to say that, okay, so with that percentage, it is acceptable, but beyond it is not acceptable, okay? All right, so of course it depends, but 1.49% generally is quite a big number. So that's the DPU and the EPMO, right? The defect per unit or the defect probability, and then we put things in the 1 million context, and then we come up with the EPMO or the DPMO. Okay, but at the end, we are interested in the sigma level, right? Remember, in Six Sigma, there are two aspects. One is a sigma measurement, and the other is how to get there, right? The how to get there is a big deal. We have to take classes before we learn how to do it. But so that's in our class context, we will focus on the sigma level, right? So what is the sigma level of this fulfillment process? So the sigma level is calculated as follows. We will do that as norm, that as dot inverse. It is an Excel equation, okay? If you use Excel, you type exactly equals norm dot as dot inverse. And then you take 1 minus the value of the DPU. When we're done with that bulky equation and with 1.5 at the end, then we have the sigma level of the process. So let's use a number and try to calculate it here and see what we have. And then I will explain why we have this equation or what it means. So we take norm dot as dot inverse, and then we take 1 minus 0.01493, right? And at the end, we add the 1.5 separately. So the bulky part right here, if you type exactly equals norm dot as dot inverse and 1 minus that 0.01493 in Excel, then you're gonna have 2.17, right? And then at the end, you would add that with 1.5. So, and finally, our calculated sigma level will be equal 3.67, right? So the sigma level, it might sound very fancy, very technical, but the sigma level in this case is just a number that can tell us how good the process is. So before I show you the explanation, let's use some phrase to say about this result. So you can either say that as the fulfillment process is operating at 3.67 sigma, right? Or you can say that in a more directly, in a more direct way, as the sigma of the process, or the sigma level of the process is 3.67, right? The higher is better. Remember, if I say that our company is operating at 6 sigma, then people will be very impressed, because in the back of their head, they understand it right away that out of 1 million units, we only have 3.4 defects, right? But if I say that, our company is operating at 3.67 sigma, right? It doesn't sound good at all, because 3.67 is very far away from 6. So 3.67 means that we will have a lot of errors or defects out of 1 million opportunities, right? So again, the sigma level is just a number to say if our company, our process is good or not. And good here means low defect probability, right? So we want the sigma to be higher, because higher sigma level means that our defect probability is lower. Okay, so that's how we calculate it. Now, how do we understand it? So for that, I would like to draw you a picture to see where actually we can see the sigma level and how is that related to the defect probability. All right, let me draw the picture for you. So the author of the equation use the standard normal distribution. All right. So for that, you would first of all draw the standard normal distribution. It is a symmetric bell-shaped curve like this, right? Where in the middle we have 0, because the standard normal distribution is center around 0. And then it goes from negative infinity all the way to positive infinity. Okay, so let's start with our standard normal distribution here. And then what we do next is we cut the right tail so that the right tail equals to the defect probability, or DPU, 0.014393, right? Or 1.49%. But remember, under the curve, we have 100%. Under the whole curve, we have 100%. So in this case, we cut a very small chunk on the right-hand side, so that chunk equals the defect probability, right? So after we cut the right tail, then we can pin down that special value. And to calculate that in Excel, you do that as norm.s.inverse, right? Then we can find that blue point, which is a 2.17 in the previous calculation, right? And after we got that blue point, we would add with 1.5, and we reach to another point. And that's our sigma level right there. 3.67 is our sigma level. Right? In this case, the sigma level is 3.67. It is far away from 6. So in a sense, we have a notion that the process is not doing very well, because probably we make quite a few errors out of 1 million opportunity for errors, right? Okay, so next, let's do some thought experiment to link the sigma level to the DPU, right? Although the sigma level is just a number, and actually we are looking at that number right here. So now we need to link that number with the defect probabilities, okay? And here's the thing. Please look at the picture. And think about the following. If DPU increases, then what will happen to the sigma level? Just think about it and then share your thought on it. If the DPU increases, what will happen to the sigma level? I got the first answer from Geraldine and then Philin, Nali. All of you agree. So it seems that, naturally you are correct. So let me show you the logic. Why do we say that, okay? And Nguyen too. Good. So here's the thing. If you look at the way we construct the sigma level, we cut the triangle and we pinned out the blue point, and then we add with 1.5, then we have the red point, right? So if the sigma level, I mean the DPU increases, this area needs to be bigger than before. For that to be bigger, then you have to cut the distribution at the lower point, right? You have to cut it, for example, here, for the triangle, for the DPU to be bigger than before. So the blue point has moved to the left-hand side. And with that, the red point also moved to the left-hand side. So the sigma level actually decreases, right? Okay, I'll answer why we add the 1.5. Okay, so when the DPU increases, it means that our process become worse than before. We will produce more errors than before, right? So to reflect that, the sigma level should decrease because the sigma level is a measurement of how good we are, our process is, right? So when the defect probability increases, then we expect that our sigma level will decrease, right? I hope it is intuitive. And then the other way around, if the DPU decreases, then it means that our process is better than before because we make fewer defects than before, right? Or we make fewer errors than before. So our measurement should go up. Then in the picture, you can see that right away. If the DPU decreases, then the triangle needs to be smaller than before. It means that the cut point, the blue point here, has to be moving to the right-hand side, right? And if the blue point moves to the right-hand side, then by the distance of 1.5, then the red point also moves to the right-hand side. So let me make the note here, the sigma level will need to increase, right? And it should be intuitive because the DPU decreases, it means that our process becomes less prone to errors than before. It should be better, and it should be measured with a higher sigma level. So now let me go back to the question by Philin. Why do we add without 1.5? So you know what? The equation of the sigma level here is just a definition. This one is a definition by the author, right? So the author defined that at the end we add with 1.5. The reason is why the author thought it is 1.5 is because of the following. If we do not add with 1.5 and we just use the the blue point as a sigma level, okay? If we just use the blue instead of the red point as a sigma level itself, right? Then if you try to achieve 6 sigma, then the blue point will go all the way to the tail to be 6.0. And at 6.0, the triangle on the right-hand side becomes so small that if you multiply that area of that triangle with 1 million, you still have a number very close to 0, which means that out of 1 million units, they produce 0 defect, right? And that's impossible. In the reality, even very high performance process, they will make 1 error from time to time. It cannot be 0. So without that 1.5, it's not realistic. So the author of the equation thought that maybe it's appropriate use an arbitrary number, 1.5, to add to the equation. So it means that even if the blue point is 4.5, right? Technically, we are not at the Six Sigma level yet. But even if we are at 4.5, but if we add with 1.5, then we say that we are at Six Sigma level. So the standard becomes less stringent than before. So it's more realistic than if we calculate this without the 1.5. Okay, so the author experiment with different numbers, and he came up with that 1.5. It's a little bit arbitrary, right? But then but over time, the equation becomes popular, and everybody just accept that 1.5, and it seems appropriate with their processes. It's not exact. Nothing is exact here. It's just a definition, and the 1.5 is just a given number, right? Arbitrary number. Okay, good. So you know what? The other way around here, the other direction is also true. If the sigma level decreases, then the DPU also increases. And if the sigma level increases, then the DPU also decreases. Okay? Philip, you are welcome. I hope everybody sees what I just explained earlier. All right, so all what we discuss here is the following. This is a one-to-one relationship. Between the defect probability and the sigma level of the process, right? So instead of the defect probabilities, now we have another way to communicate how good our process is. In the reality, if we talk about, so another question is, why do we just use the defect probability, right? And then why do we do not need the sigma level if we just talk about the defect probability? But then think about it. Some process, they have a defect probability of 0.0000, several zeros before they get an actual number, right? Then if you talk like that with your customers, with your clients, do we expect the customer to remember a number of zeros? No, right? So that's why they tend to simplify it, and then at the end, somebody comes up with an equation to convert the defect probability to just a regular number, so that we can easily remember, we can easily communicate that number with everybody, including our clients, our partners, our bosses, our colleagues, with everybody, right? So it's just for the convenience of communication. So that's the sigma level. And along our discussion here, we do not talk about any specific company, any industry, nothing, because it's generally defined, right? It's broadly defined. It doesn't depends on the individual industries or companies. So it means that we can apply this to any processes, any process that you pay attention to, as long as you can calculate the DPU, then you can convert that to the sigma level right away, right? Okay, so we can use this sigma level to also characterize the efficiency of a worker. For example, if we talk about an accountant, in his or her life of work, they will have to calculate millions of numbers. Out of 1 million, if they only make 3.4 errors, think about it, they are at the Six Sigma level, right? And if you are an accountant, if you can write that sentence, one sentence, or just a small phrase in your CV saying that you are at the Six Sigma level, people will interview you right away, okay? And they will pay a lot of money to hire you because it's exceptional, right? Okay, if you are an IT guy, you write out 1 million lines of code, and among 1 million lines of code, you only have 3.4 lines with errors. Then they will sick you out. They will pay you a lot of money to work for them. Okay, so the sigma level can be used to characterize many things: processes, companies, people, workers, things like that, right? All right, so that's the sigma level. All right, so we're done with part A, and now let's do part B and C. I say part B and C because they are quite similar. Let me show you part B and C first, and then we work on them. All right, so in part B, to achieve a calculated sigma level of 4.0, what would have been the number of errors, right? So, and similarly, in part C, assume that the fulfillment service is actually a 5.0 sigma. Then what would have been the theoretical number of errors? So B and C are quite similar. To answer B and C, then we're gonna use the second table right here. The first equation, we do not need it because we just use Excel to calculate the norm that has the inverse function, and then we get the sigma level, right? But for the B and C questions, you will need to use the lookup table here. This lookup table is the following. If we are operating at 2.0 sigma, right, then out of 1 million units, we're going to have 308,000 defects, right? It's a huge number of defects. But if we improve our process better to be at 3.0, then we can drastically reduce the number of errors, right? Only to 66,807 errors. But that's still big. If we invest, we improve our process to be even better. We are at 4.0, then out of 1 million, we only have 6,209, right? Earlier, we calculated to be 3.67. So we are closing to that end rather than that big end, right? But from 3.67 to 4.0 is still a long way to go, right? So, but if companies, they invest much more, they will reach 5.0. Then out of 1 million units, they only have 232 defects. And of course, if some company, they have to work at the Six Sigma level, right? Or 6.0 sigma, or even more, 6.1, 6.2, it can be any decimal number. Then they have to invest much, much more. And then out of 1 million units, they only have 3.4 defects, right? So it's a very impressive process with near zero defects. They have to spend a lot of money and efforts in it. Better design of the process, better equipment, better trained workers, right? So a lot of things have to be better to climb up the sigma ladder. To climb up the sigma ladder, everything has to be better. Okay, so we're gonna use this lookup table to answer B and C. I'm gonna show you that right away. Okay, so let's go to part B. In part B, we want the calculated sigma level to be 4.0. In this case, we need to calculate the number of errors. Okay, so if we look at the lookup table at 4.0 sigma, then we know that out of 1 million opportunities are off, we're going to have 6,000. I'm looking at that table right now because it is given, you know what, in the homework, in the exam, if I give this question to you, I always include that lookup table. Right? We don't have to memorize this at all. So out of 1 million opportunities, we're going to have 6,209 errors. So the question is, if we have 1,406.25 ops or orders or shipments in our current context. Okay, then how many errors we would see? Right, so that's the question. So it's not that difficult, right? We just do it proportionally. Then we should be able to find the number of errors. So we write that as the number of errors divided by 6,209.7. Then proportionally, that should be equal 1,406.25 divided by 1 million. Right? It should make sense by now. So out of 1 million, we have 6,209. Then out of 1,406, then we should have this number of errors. So the ratio here should equal that ratio over there, right? And to solve for this, we just rearrange the terms. The number of errors would be equal 1,406.25 divided by 1 million, multiply with that 6,209.7, right? We just cross multiply to the other side, and then because to the other side has to be flipped up, right? If it is at the bottom here, it has to be flipped up to the other side. So we cross multiply. That's why we call it as cross multiply. And then the answer here is, we have the answer. So it should be 8.73, right? Errors. So if we want to operate at 4.0, then on average, we should have 8.73 errors. It means that sometimes we see 8 errors, sometimes we see 9 errors, sometimes we see 10 errors, right? But if we average over the cycles of operation, is about 8.73 errors. Then our calculated sigma level is going to be 4.0, right? So we do it proportionally, then we can achieve that 4.0. Okay, so that's part B. And part C is very similar. Let me do that quickly. In part C, we assume that we are at the sigma level of 5.0. So what would be the number of errors? One more time, we look at the lookup table, right? Out of 1 million opportunities, we will see 232.6. Earlier it is 6,000 because we are at a 4.0 level. We are lower, right? Earlier. But now we are at a higher level, 5.0, so the number of errors will be smaller than before. So out of 1 million, we expect to see 232.6 errors. So if we only have 1,406.25 opportunities, I'm sorry, I missed the word opportunities here, then how many errors we expect to see? All right, so it's quite similar to what we did earlier. So proportionally, the number of errors in this case divided by that 232.6 should be equal to 1,406.25 divided by 1 million, right? And then one more time, we just cross multiply the number of errors in this case will be 1,406.25 divided by 1 million, multiply with 232.6. So it should be, we have 0.32, right? So out of 1,406 units, we expect 0.32 errors. It means that sometimes we see 0 errors, sometimes we see 1 errors, sometimes we see 2 errors or more, right? But if we average over the cycles of operation, then the average number is 0.32. Okay, so in the homework question, I ask you a question that can we see this number of errors in real life? We cannot, right? Because either we see 0 or see 1 or see 2 or see 3, right? Or if we talk about the number of errors, then the least that we can see is 1. We cannot see a decimal number of errors like this. All right, so let me make a note here. We cannot see this number of errors in reality. The 0.32 here is just an average number. And it is smaller than 1, right? We never see anything, an error that is smaller than 1. Either we only have 1 error or 2 errors or 3 errors, right? So, here's the thing. Part D is just a continuation of part C, and it goes as follows. So in part D, what is the number, the lowest number of errors that might happen, right? Then that is going to be 1. If we see errors, then the lowest number of errors will be 1. It can be 0.32. So instead of 0.32, now we see 1 error, and that will make the defect probability is higher than it's supposed to be, right? So that will lead to misleading measurement of the sigma level. So in this case, we need to calculate the new DPU. Again, it is the number of errors divided by the number of opportunities. So we take 1 divided by 1406.25, and that's going to be 0.0071, right? Look at this number, it's very small. If you try to remember this and talk to the customers, right, it's really hard for everybody to grasp the same number. So that's why we have to convert it to the Six Sigma level. By the way, along the way, I also asked you to calculate the EPMO of this DPU. Then I believe you can do that by yourself. Right? It's just that calculation. We are more interested in the sigma level here. The sigma level is going to be norm dot as dot inverse, the same equation as before. But we put in 1 minus the new DPU, right? And we add with 1.5 at the end. With the new DPU, now we have the blue dot to be 3.19, and then plus with 1.5, right? So the calculated sigma level, yeah, so I would say that this is a calculated sigma level, is going to be 4.69, right? This number is smaller than 5.0. We assume that we are operating at 5.0, but the calculated sigma level is significantly less than 5.0. You might think 4.69 is close to 5.0, but actually it's significantly lower than 5.0. So because of these, we call that as a misleading results. Misleading measurement. And the reason is we have a small sample here. When we have small samples, if we see 1 error, then might be 1 error is way more than the 0.32, right? So when we calculate the sigma level, it's going to be significantly lower than the actual or the underlying sigma level, right? It's supposed to be 5.0 or close around that 5.0, but here we have 4.69. So it's way lower, right? so we call that as a misleading measurement because we have a small sample. In this case, why do we have a small sample? Because it costs money to contact more customers. You have to hire more people to survey the workers and then collect the data and then do all of the calculation, right? So in this case, might be the company want to save money. On this end, they do not want to spend too much, right? So they only contacted this number of customers and then 75% of them answer you. And at the end, we only have a small sample of 1,406 orders, right? Okay, so the next question is, in part E, then what would be the sample size that might generate one error rather than 0.32 errors, right? So what would be the sample that is big enough for us to see one error out of it? Then that's the question E. So in this case, right, the number of errors is 1. And we are at the 5 sigma level, 5.0 segment. So what would be the sample size that big enough to see that one error? So the calculation is quite similar to what we did in BNC, right? So out of 1 million opportunities, we expect to see 232.6 errors. Here we talk about fulfillment services, about order shipment, right? That's why we call them as errors. In manufacturing, we will call them as a number of defects. All right, so we have one error. Then how many opportunities there are for us to see that one error? Right. So we one more time we can do that proportionally. So the number of ops, the number of ops divided by 1 million equals 1 divided by 232.6, right? So the number of the sample size should be 1 million. You just cross multiply it like before, divided by 232.6. Then you would have it's a decimal number, but we can round it to be, roughly speaking, to be 4,300, right? So so units, or in this case, we need to have a sample of 4,300 orders. And out of these 4,300 orders, we expect to see one error, right? Rather than earlier, we cannot see one error. We only see 0.32 errors, and that's not realistic. All right, but then to have this sample size, you have to contact more people than that because only 75% of the customer would answer you, right? So the number of contacts would be 4,300 divided by 0.75, right? So that if you multiply 0.75 with the number of contacts, you're gonna have by 4,300. So eventually the answer would be 5,734 customers. All right, so we need to contact 5,734 customers. 75% of them will answer you. So eventually we have a sample of 4,300 data points. And then with that sample of 4,300 units, on average, we're gonna see one error coming out of it. We are operating at the 5.0 sigma level, right? So that's the That's the calculation in part E. And with that, we are done with the homework question. So I hope that after some practice exactly like this, right, with that question 21, then you should be ready if I ask you this in the exam. We have very little time left. Let me show you what we got on Canvas in preparation for the midterm exam. All right, so if you go to Canvas, right, on the exam day, you should click on assignments. And then on the right-hand side, the top corner right here, you should click on show by type, because show by date will break up the folders, will break up the structure, right? So you should click on show by type, and then right at the top, you're going to see the midterm exam folder. And in that, now you can see the preparation, you can see the instruction. So on the exam day, you're going to see the instruction, right? You can check the instruction now. And then on the exam day, these 3 links will be active. So you click on each one of them, answer them, and then before the end, the due date somewhere here, you would need to click submit, right? Then you should be good with the exam. So 1 through 10 are multiple choices. 11 and 12 are value submission only. Right? That's why I put it right here. You don't have to upload anything. 13 and 14, you need to handwrite it and then upload the PDF file at the end, right? So those are the 3 actual links for the exams. They are locked now, right? If you click on that, they are not active yet. Okay, so in preparation for the exam, I recommend you to click on that midterm exam preparation. You're gonna see the study guide, which is right here, right? And then the review for midterm exam, which is right here. After you submit question 22 today and tomorrow, I will give you the answer to question 22, so that everybody should be on the same page. I still have my office hours tomorrow at 10 to 11, and also on Wednesday from 9:30 to 10:30, right? So if you are not clear about anything, please feel free to see me on Zoom during my office hours. Right, so, oh, by the way, remember that even though our class start at 1 p.m., but the exam can be started 5 minutes early, right? You can see the 12:55 right here. So you can actually start the exam at 12:55 p.m. Right. So I'm open to questions. Right, our class ends at 2:15. Please feel free to take off. But if you have questions, please feel free to stay back and ask me the question. So everybody, please, good luck with the exam. Okay, it's like what we do in the homework. It's nothing more than that. I will try to make it shorter, right? Because the homework questions are very long. So in the exam, I try to make it shorter. So don't be surprised if I cut this part or cut that part of the homework question to give you in the exam. Any question for me at this point? You're good? Okay, so we end our class here today. So thank you and good luck with the exam. So okay, good. So if you still have questions, right, please feel free to stay back a little bit.